In this video, we're going to talk about something very interesting and something that uses vectors in its definition. So we're going to talk about equations of planes in 3 dimensions. So just to draw an analogy with straight lines in 2 dimensions, we know that in 2 dimensions we can define a straight line simply by some equation like y equals to mx plus b. So m tells us the gradient of that line, and b tells us at which point the line crosses the y-axis. So we can also express this in terms of ax plus by plus c equals to 0. So that's another way in which we can draw, or we can write, the equation of a line. Now, what happens now is that what if we want to bring something to the 3rd dimension? So let's say now we want to, instead of drawing just a straight line, we want to draw a plane. So let's say we draw a plane like this. And you can imagine that this plane is going to extend to infinity in all directions. So just in the same way this line extends to infinity in both directions. So we want to know, how do we find the equation of a plane like this? How do we actually specify every single point on that plane in a compact equation like this? Well, it turns out that it's a little bit more complicated than this, because in this case, you can imagine that you're going to have a whole set of points, and you can just specify 2 of them. So in the case of a line, if you know 2 points that lie on that line, you can find the equation of the line, because you know this is going to give you the gradient, and you know the line passes through both of them, so you can use those to derive the equation of the line. In the case of a plane, if we had just 2 points, so let's say I just have 2 points here. Let me just get rid of this. And I'm gonna draw this in blue so that you can see it better. So let's say I have a point here, and I have a point over here, and now we draw some straight line between them. And you might say, well, if the 2 points pass through this line, and this line lies on that plane, then maybe that can actually be useful for finding the equation of the plane, shouldn't it? But the problem is, if the plane is actually crossing that line, then this plane is actually allowed to rotate about that line. So we don't actually know. We know the orientation of the plane along that line, but we don't know the orientation of the plane with respect to it, because this plane could very well rotate about that whole line. So how do we actually confine this? Well, it turns out that if we add a 3rd point, say somewhere there, and then we draw another line there, then we essentially confine the plane, because the plane is now not allowed to rotate across that line, because it is now confined by this line, and it is not allowed to rotate about this line because it is now confined by that one. So it is essentially locked in space by 2 lines. Now, obviously, finding those lines in 3 dimensions is a very hard task, but what I can do instead is I can find 2 vectors. And they don't have to be these 2. It could be this one, it could be these 2, or these 2, or whatever. As long as you have 2 vectors that go from one point to the other, and then from one point to another, then you can essentially define the orientation of the plane. Because if you take the cross product of those 2 vectors, you get a normal vector, and that normal vector is going to be perpendicular to both. And if it is perpendicular to both, we know that it is going to be perpendicular to the whole plane. So we are going to define the equation of the plane as follows. We're going to have some normal vector. So basically this normal vector is going to be pointing perpendicular to the plane. And now we're going to take the dot product with some position vectors. So you can imagine if we start from the origin and we point towards some point that lies on that plane, let's call it P, and this is R. Then by doing this, we know that this is the same as saying this. We can actually find the equation of the line, because we're going to have a scalar sum of variables. So now what we do is we define n as being a, b, and c. Then r is going to be the following. We're going to have x minus x naught. So basically we're going to have this kind of equation, because we know that that's the same way in which we would define it in 2 dimensions. We have some shift in each of the coordinates. And then if we carry out this cross product, we're gonna get the following: ax minus x naught plus b y minus y naught plus c z minus z naught equals to 0. So this is in essence the equation of a plane. So all we need to do is, well, first of all, we need to know the locations of at least 3 points that lie on that plane. Then we create 2 vectors that go from one point to another, take the cross product to get n, and then that n is going to give us the coefficients a, b, and c. And then for this equation here, all we need to do is we need to put in the coordinates of one of those points. And in general, you will put the coordinates of a point that you didn't use to calculate n. So let's do an example now, just so that you can understand what's happening here. So let's go into an example. So let's say I give you the following points. Let's say p equals to 1 minus 2, 0. Then q is going to be 3, 1, 4. And then r is going to be 0, minus 1, 2. So the first thing we're going to do is we need to create 2 vectors. So how do we do that? Well, we know that we can create a vector from one point to another. So let's say PQ. And this is going to be a vector by simply subtracting the endpoints minus, subtracting the starting point from the endpoint. So if we're going from P to Q, Q is the endpoint, P is the starting point. So we're going to subtract this from that. So we're going to have 2. Because we have 3 minus 1 is 2. Then 1 minus minus 2, that's 3. And then we have 4 minus 0, that's 4. So this is a vector that points in the direction from P to Q. Now we need another vector, so let's define PR. So we're going from P to R, so basically we have 0 minus 1, that's minus 1. Minus 1 minus minus 2, that's plus 1 in total, so that's plus 1. And then 2 minus 0, that's just 2. Okay, so now all we need to do is calculate our vector n, which is just the cross product of those two. So we have PQ cross with PR. So let's see what we get. We're gonna do the multiplication here very quickly. So the first component is going to be 3 times 2. So that's 6 minus 4 times 1. So that's 6 minus 4, that's 2. Then for the second one, we're going to have 2 times 2, that's 4. Minus, so it's minus 4, so that's 8. But remember, the second component here, the jth component is always negative, so that becomes minus 8. And then for the kth component, we have 2 times 1, that's 2. Minus 3 times minus 1, so basically that's going to be plus 5. So this is our unit vector, not a unit vector, but our vector pointed perpendicular to the plane. Now that we have that, what we can do is we can put that into the equation. So we have A, B, and C. So we're going to start off as this. So we're going to have 2x minus x naught plus, well, this would be minus 8. So minus 8 y minus y naught plus 5 z minus z naught equals to 0. And now in here, what we're going to put is the points of one of the coordinates that we had. So one of the things that we can do is we can just grab a set of points that we already had. So we can either put in this one or this one or this one. We're going to do this one. So let's have P in here. Going to have 2x minus 1. So that's x minus 1. Minus 8 y plus 2. And then plus 5 z minus 0 is equals to 0. And now if we expand this out, we should get 2x minus 8y plus 5z equals to 18. So this is our general equation of this plane. So we chose the point P because it was the point that was common between the two vectors. So in general, when we put the coordinates of a point, we choose the one that we chose the two vectors starting at. So our two vectors started at P. So that means that we choose this to put into the equation of the plane. And that's it. That's how you define the equation of a plane. And that's how you specify an orientation by using the cross product of two vectors. You need at least 3 points to properly define the orientation of a plane. And this is a really nice application of the cross product of two vectors, as we have seen. So vectors are really important in both geometry and physics, as we'll see in some later examples as well.